Hello student, welcome to today's session. So today we will be discussing some questions based on the topic of stability of resonating structures and stability of carbocation. These questions I have picked from the book of MS Chauhan sir's book of the organic chemistry, and these are some of the questions which you have sent in the last 1 week, and I consolidated them together from one topic, and let's discuss one by one all of these. So here, the stability of resonating structure of this particular structure is being given, for which all the resonating structures are being given, for which you have to tell the stability. One is this, second is this is the entity on which H positive is going to attack, and you have to see which site is the best one. And last is the stability of the carbocation. So let us discuss one by one these questions. So as regard to the first question which is there in front of us is that this molecule is being given for which the resonating structures are being made. So one resonating structure, they made it like this lone pair goes here, this goes here, and this is the first one, first resonating structure. And the second, which they have turned it like this way, this goes like this, and this is the second resonating structure which we get. And the third one is the one they have shown it like this, that this pi bond happens to go here. If I would do it like this with the red marker, so this is the third, or rather I would say this is the third one. And the fourth one they have shown is the pos let me show it with the green marker. So this goes here and this goes here. So in that sense, this is the last resonating structure. So out of these all resonating structure, we have to pick which is the best one, which is the most stable one. So among the resonating structure, what I always simply say to my students that because during making of a resonating structure, you cannot change the position of the atoms. The sigma bonds would remain as such. Only thing which you can change is the pi bonds. There is delocalization through the pi bond. So I simply say it as more are the number of covalent bonds, more is the stability. And more number of covalent bonds, the covalent bonds are of two types, sigma and pi. Sigma always remains same, and this can change. Pi bonds can change. So more number of pi bonds if you have in a structure, more is the stability. Second is, if this first point is not able to give you the right answer to the problem, then you have to look for the second point. Second point is that those resonating structures become exceptionally stable in which the octet of all the elements is complete. Even if a electronegative element carries a positive charge, then also it is quite stable if the octet of all the elements is complete. Or a resonating structure engages, because of the resonance there is attainment of some aromatic character, then also it is quite stable. And last, if in the resonating structure there are some charges, we would love to keep like charges as distant apart as possible, and unlike charges as close as we can. So that way it would increase the stability. So these are the fundamentally 2-3 points which you always have to keep in mind while evaluating the stability of the resonating structures. So let us do the first question first. Now in this case, if you could see in the first structure, if I would say this particular structure, here you have 5 pi bonds, isn't it? And here also you have 5 pi bonds, here also you have 5 pi bonds, here you would get 4 pi bonds and 5 pi bonds. So if I keep myself to the point of first point, that more number of covalent bonds, more is the stability. So that means A, B, D would be the right answer, and we have to select one among these. So that means the first point in itself is not giving me the right answer to this particular problem. Although this is quite important, and if in case in among the resonating structure number of covalent bonds, or for that matter number of pi bonds becomes equal, then you have to go for the next one. Now let's see the next one. In the next one, I can see categorically, if I would say in the second one, in this one, in the second one, in the second part, if you could see simply that this particular structure which they have made has made the two entities aromatic. This is beautiful. Both of that has become aromatic. Now just let me show it the way I wanted to show you. So now see here, if I will bring this lone pair here and this bond goes here, what next structure do I get here? The next structure do I get here is something like this, oxygen, and here you would get, oh sorry, so it is to be made like this would get something like this would get a negative charge, and here you would get a positive charge because one of the lone pair came here, and still you are having one lone pair on this oxygen, and these two electrons came here. Now if you could see, the viewpoint here is that in this resonating structure, this part has become aromatic, and so is this part has become aromatic. So simply they attained the aromatic character. Second thing is that the octet of all the elements is complete. If you would see watchfully, that the octet of this oxygen is complete, as well as octet of this carbon is also complete. So octet of all the elements is complete. Octet of all the elements is complete. So that also is driving me towards the B answer. And both of these things have become aromatic as well. So that is very important. So aromaticity brought the stability into this. Now the point here is that if in case I just would rely on the second point, that the octet of all the elements is complete, then you can challenge me with the A answer as well, because here also the octet is complete, here also the octet is complete. But here you would not be getting the aromatic character at the lower end of this part. So here this has become aromatic, this also has become aromatic. So I think I made my point clear. The B would be the right answer for this particular question. Let's move on to the second problem. Now in this question, what you are supposed to tell is that if in case you attack it with H positive, where would be the attack of H positive be possible? Would it be possible on this lone pair or this lone pair, or simply it would attack on a pi bond? So they attacked in all the aspects. So what way they have done is, one, they have taken it like this, that if you have this thing with you, and if I just would attack on to this H positive here, the structure which I would receive is this one. And if I just would attack H positive here, then this pi bond would come here, then you would get this one. Or they have attacked onto the lone pair of the oxygen, which is this one. If, because I have two oxygen atoms here, so if H positive attacks here the onto the lone pair, then you would get a bond formation here. So which way it should go? Now if I would consider the first one, A option, if I consider this one as an option, what I am able to see here is that once the attack has happened, this is the positive charge and this is the pi bond. Once the attack has happened, this definitely, this oxygen's lone pair is going to provide it a stability through resonance. And once this stability came, and the octet of all the elements would become complete. The octet of all the elements would become complete, isn't it? So this can be one of our answer. A could be one of the answer. But if you would see the B option here, the positive charge here, this positive charge is not being stabilized. Reason being, CO group is an electron withdrawing group. It would not be stabilized this carbocation. So considering the fact A and B, if I just would see A and B, A would be the right attack. Now let me go into the C option. In the C option, what you are able to see here is that once the attack has happened, what you are able to see here is that you would get a positive charge onto this oxygen with one lone pair still there. And here also you could see that the octet of this element is complete. Oxygen is carrying a positive charge, still it is quite stable because its octet is complete. Now what is the very interesting point here is that this oxygen also do have a lone pair, and this is in conjugation. Just see it with me. This goes here, this goes here, and this goes here. Wow. So this in a way shows a resonance in a loop. This resonance is happening. This is more extent, the resonance is in the loop, which would provide it a greater stability. And once I do the resonating structure out of this, what another structure I would be getting here is positive on this one, and you would see that here I have achieved a sort of aromatic character. Here you are able to see a aromaticity attained here. So aromatic character came into the point. So this way, this would be the most significant attack has to happen onto this oxygen rather than the oxygen which is there in this part. Because if I would attack onto this oxygen, what another structure which I would get here is somewhat like this. I would get a lone pair and the oxygen this positive would come here and positive charge here. Now this positive charge would not undergo delocalization just like the first one, the C option one. This positive goes here, and the next structure which you would receive is somewhat like this. This pi bond comes here. It would not be possible, which generally would be a mistake done by most of us, that you just would engage resonance like this, because here the oxygen cannot exceed its covalency above, because this now has become 10 electrons, because still it is having a lone pair and one more lone pair here, and you have created another pi bond here, which in a way makes 10 electrons. So this would not be possible. So this in a way shows that the C would be the right answer for this option. So C is the answer for this particular question, because the oxygen got a positive charge, and because of the delocalization you have achieved a aromatic character. So this is one answer which you should be clear about. Another one is that which of the following is the most stabilized carbocation, because I consolidated all the questions in one way where you would see the same entity applied in all these questions. So in this question also, now you could see that this is a primary carbocation. This is a primary carbocation because the carbon carrying a positive charge is attached to one carbon, and which is allylic also. This is allylic carbocation. Allylic in the sense that positive charge is in conjugation with pi bond. So this can undergo resonance. Same is the case here. This, if you consider this one, this is a tertiary carbocation because the carbon carrying a positive charge is attached to 3 carbon, but there is, here you would find there is resonance taking place. The resonance is possible, but here you would not find any resonance. Only thing which you can get is the hyperconjugation. And the last one is, the third one is this one. So here it is again a tertiary carbocation with allylic carbocation. Allylic in the sense that the positive charge next to the double bond which can undergo resonance. And now let's see the last one. Last one is also the tertiary carbocation, and this tertiary carbocation do engage the lone pair of the oxygen. That is very interesting to show here. So here, how could I show it? If this lone pair goes here, this bond goes here. So it engages the lone pair of oxygen of the methoxy, which creates an extra pi bond here. Or if you would want to go step by step, we can show it like this. And another thing which you can see here is the positive charge conjugation can happen from this direction also. So there is more involvement of resonance taking place, more number of resonating structures do I get. Now let me show it in stepwise, that if I would say this is the entity which I have received, because if I would do it like this, the positive charge comes here, the first one, this part only. If I just engages this one, so the positive charge comes here. Now this positive charge can be stabilized by the lone pair of this oxygen, and as a consequence next structure you would achieve here is something like this. So you would get a double bond here, as well as now you would get a positive charge here. Now this particular resonating structure is again exceptionally stable. This is exceptionally stable. Why is it exceptionally stable? Exceptionally stable simply because of the fact that it is having the octet complete of all the elements. So that is why we would be saying that which out of this is most stabilized carbocation. I would be saying D would be the right answer. I hope you have understood all these three questions where carbocation stability or resonance, how it is being used to, how is it being applied to find the stability of entities, is a quite a important one. So hope to see you in the next session where we will be doing some more questions in regard to the organic part. Thanks a lot. Have a nice day. Stay safe.